Yes, I'm ready.
Good, yeah.
Okay, thank you. Good morning, everyone. So in the last few days, we've learned and discussed a lot about natural systems like earthquakes, landslides, volcanoes a little bit, and also about the dynamics happening at different scales, at microscale, essentially, in geomaterials like rocks. And in this time slot, I'm going to take a small detour to address one of the problems happening in urban systems, which I think they are also at some extent important. So yeah, I'm doing this. So by no means this work is only made by me, and I also want to take the opportunity to acknowledge the contribution and valuable comments of some more people that also is taking part in this ITN. So this is about structural health monitoring and damage assessment in civil structures. Especially, this is about spotting internal damage footprints in concrete structures. But perhaps the most arguable term in this presentation is exactly this one, because damage detection is not a trivial task to perform. The complexity level of solids related to their heterogeneity and isotropy, as well as inaccuracies in the definition of damage, make damage assessment even more challenging. However, the analysis of variations of elastic properties through the time and at different stress conditions has shed some light on this problem. In laboratory setups, it has been observed an important sensitivity of time and stress-dependent elastic properties in solids like polymers, steel, rocks, damaged solids, and concrete. As a result, various models have been suggested to explain this phenomena, also known as nonlinear mesoscopic elasticity. And in this project specifically, we are trying to observe and incorporate all those models to damage assessment in civil structures. Specifically, we're analyzing one of them also known as acoustoelastic effect, which is part of the stress-dependent elastic effects, and the relaxation process that is part of the time-dependent effects. But the main question we are trying to answer with this project is if we can identify internal damage in real condition concrete structures by using two main ingredients. The first one is wave field-based methodologies, and the second one is, of course, the nonlinear mesoscopic elasticity models, which is essentially the relationship between the physical state of concrete structures and some possible variations in the behavior of these specific models. Just to give you an idea about where this project is located in this ITN, so the day before yesterday, we observed like this laboratory experiments by Declan in this very small specimen. We also observed this analysis of healing and damage processes in a bit larger, I don't know specifically the sample size, but a bit, sorry?
10 centimeters higher.
All right, there you go. So sample, and then I'm going to work with this a bit larger sample here, which is, is this structure. So this structure is the blade structure. This is a 24-meter long reinforced concrete test bridge. This is located at BAM facilities, and we performed this experiment in collaboration with BAM and LMU. In this experiment, we recorded information at different frequency bands. So we recorded wave propagation at different frequency bands using different type of sensors. The first one is 6-component sensors. We use these sensors to record acceleration in 3 components and angular velocity in 3 more components. Then we also use the conventional geophones and the DSS system with a fiber optic cable in 4 different segments, 2 segments on top of the bridge and the other one in the bottom of the beam. Today, I'm going to talk about the information we recorded with embedded ultrasound sensors, which is information recorded in the ultrasound regime, and most of the content of this presentation is going to be about results obtained with these sensors. So this is a 3D representation of the bridge. Let's take a zoom-in view in the north span of the bridge. Here you can see the geometry and where precisely are located the embedded ultrasound transducers. So let's rotate these figures, and you can see with respect to the north, the location of the pair located in the south left side. So we have transducer and receiver, south right, north left, and north right. So in total, we are using 4 pairs of embedded ultrasound transducers, and I'm going to use the same color code in what follows to refer to information and results obtained with this information. So this is about the experiment we designed, and so I forgot to mention that this concrete beam is equipped with a pretension system, and we use this pretension system to compress the structure in its longitudinal direction in a controlled manner. So we started compressing the bridge with a force of 400 kilonewtons. We started recording information in the north side of the bridge. First, we recorded 1 minute of baseline information to capture the effect of the pre-stressing system. After this 1 minute, we did a hammer hit in the north side of the bridge. Then 5 more minutes of relaxation process. After these 5 more minutes, a second hammer hit, 5 more minutes for relaxation, and the third hammer hit, and finally, the last 5 minutes for relaxation process. After this, we turned off the acquisition system in the north side. We moved to the south side, and we essentially did the same thing. 1 minute of baseline information, the first hammer hit, 5 minutes of relaxation process, second hammer hit, 5 minutes of relaxation process, third hammer hit, and 5 minutes of relaxation process. After this, we turned off the acquisition system, and we changed the pretension in the bridge. We decreased the pretension to 370 kilonewtons, and we did essentially the same thing. So we recorded the same information in the north side, and then in the south side. So in general, this is how the experiment looks like, at least the part that I just showed you. But this is all the experiment that we perform in that moment. And of course, we took a small lunch break at around noon. So yeah, you will see the effect of this lunch break in what follows. This is really, really important. So yeah, as I mentioned, we are analyzing 2 different effects. The first one is the acoustoelastic effect, which is essentially how much the structure or the elastic properties of concrete are changing when the stress conditions are changing as well in the specimen. So we have again the experimental setup, and we use the information recorded in the 1 minute baseline information. So we perform Coda wave interferometry stretching method to analyze the relative dB over V, relative velocity changes. And we use as a reference the information recorded at the beginning of the experiment as deformed the states, the subsequent information. This is the time window we use to perform this analysis. And here you can see the results. So here what you observe in the vertical axis is dB over V, and in the horizontal axis is the stress state in the beam. So you observe the the results for the 4 different locations, south left, south right, north left, and north right. Here you can observe that this acoustoelastic effect is behaving mostly linear, and this linear model is essentially giving information about something called the acoustoelastic constant, which is essentially the slope of this linear model. So here you can observe the slope obtained in the 4 different locations. We can do the same thing, the same analysis when we recompress the structure. We can obtain again the linear fitting and also the slope of each linear model. So in this moment, we can observe that there is this sort of anomaly happening in the north left side of the bridge, where this slope or this acoustoelastic effect is larger than in the other locations in the bridge. So it was about acoustoelastic effect. And I'm going to talk a bit about this relaxation process, that is essentially the recovery process on the elastic properties after the medium or the specimen has been perturbed. And this is described essentially by 2 two main effects. The first one is a drop in the elastic properties, and then the subsequent recovery process happening. To analyze this phenomena, what we did is, again, Kodak wave interferometry, but in this case, we changed the setup. So the reference is still the 1 minute of baseline information, and the deformed states corresponds to the subsequent hammer hits after this 1 minute of baseline information. We did the same thing for north side and also for south side. We used this time window to analyze this information, and here's what we obtained. So at the beginning of this figure, you can observe like a sort of, like in this part, you can observe like the effect of the 1 minute of baseline information, and then the effect of the subsequent hammer hits, which is the drop in the elastic properties of the concrete, and then this sort of a bit weird recovery process. This is for north left, this is for north right, south left, and south right. But then what happens if we do the same for all the experiment, which means like, performing the same analysis for all the pre-stressing forces? And this is what we obtain. So here what we observe is a bunch of information, so a lot of different recovering processes happening in the structure. And early I mentioned the effect of the lunch break, and this is observed here essentially. So we changed the pre-stressing force in the bridge, and then we decided to take a small break to have some food. And they forgot to turn off the recording system, and this is what we recorded. So it's going to be useful for future analysis and interpretation. I'll let you know why. So let's take a zoom in this part of the figure, which corresponds to this thing. So in the vertical axis, again, dB over V, in the horizontal axis, time. And in order to describe what is happening here, we have to identify which elements are present in this plot. So in this case, we can observe three sort of relaxation functions happening. And in order to describe this phenomena, we use the same relaxation function that Manuel used from Snider and Schoenfelder in 2017. This relaxation function is sensitive to three different parameters: tau mean with minimum relaxation time, maximum relaxation time, and the amplitude or the velocity drop of this phenomenon. Also, we can observe this sort of linear effect happening along this along the time. In this case, we don't have like a solid explanation about where this linear effect is coming from, but we're interested in analyzing how much this is affecting the relaxation processes. In this case, the slope of this linear effect. And of course, the remaining effect of the second hammer hit, which is described by this sort of step function happening only in the second hammer hit, and the remaining effect of the second strike present only in the third strike by means of this step function. So what happens if we sum all these elements is essentially this thing. And in this case, now we have this analytical model. We have observations, and the rest is to perform this sort of linear inversion process in order to recover like these four different elements that you observe here. Just to recall, is the amplitude of the relaxation functions, the slope of the linear effect, the amplitude of these two step functions. So for this specific case, you can observe the model obtained by means of Monte Carlo methods, and this is the results that we obtained for the four different variables we are interested in. This is the standard deviation of the model. And of course, we can do, these results corresponds to this specific compression state. But we can do the same for all the experiment. So in this case, you observe the results of the velocity drops for all the pre-stressing forces. This is the effect of the linear effect. the remaining effect of the first strike and the remaining effect of the second strike. And this corresponds to the south left side. We can do the same for south right, north left, and north right. And this is essentially what we obtain. So we can sort of extract interesting behaviors happening here. Like, for example, in the south side, we observe some sort of symmetry, some sort of symmetry in the velocity drops obtained while decompressing and while compressing. This is a behavior that we cannot observe in the north side. In terms of magnitude, we observe that the north side have like larger magnitudes in velocity drops, also in the slope of this linear effect. And the behavior of the remaining effects is a bit random, but it seems to be larger in the south side. So yeah, as for the conclusions, as we observed, the acoustoelastic effect is larger in the north side, specifically the north left. The velocity drops in terms of magnitude are larger also in the north span of the bridge. The linear effect as well is larger in the same span, whereas for the remaining effects, we observe this random thing happening, but still, in terms of magnitude, this is larger in the south side of the bridge. I have to mention that there is some evidence of external cracks in the north side of the bridge, which exactly corresponds with the side where we observe larger effects of these nonlinear mesoscopic elasticity models. And in this case, we can sort of say that the sensitivity of nonlinear elasticity models on real condition concrete structures is still present in this type of structures, and is sensitive to the presence of damage. So it is in agreement with the observations that has been obtained in laboratory setups. But still, we have sort of open questions, and I would like to have some feedback from you, if possible. So the first one is to see what is happening when we change the pretension in the bridge. In some cases, we observe this sort of a scatter pattern in the 1 minute of baseline information. We are not sure what is happening there. We also have different relaxation processes for the same pre-stressing state, which sort of gives an idea about how relevant is the previous history of the deformation in the bridge. And also we are not sure, so we are able to characterize, but we are not sure what causes this downward turn in the relaxation curves. And in general, so the goal would be to infer a physical model that relates the microscale dynamics to the microscale behavior using the observations that we have in this specimen. And the next question is, what is the relevance of the spatial variations at material scale in the dynamics at the structural scale, which means how relevant are the variations that we obtained, that we observed in this part of the bridge from the perspective of the low frequency data, which means the information of the recorded by the 6C sensors and the geophones. So yeah, in that sense, how we can link the behavior in the small scale to the structural scale. And that's it. Thank you.